Okay, so today this is going to be our last lecture on time series. And typically, actually, there's nothing really new in today's lecture. I mean, there might be some terms that looks like new, but actually the intuition and the underlying concept, the theory, it's just basically extending what we've seen earlier in regression where we have only one time series or sort of related back to what we've done in semester 1 in topic 1 and topic 2. And you'll see that, so basically today we're going to talk about how we model two time series in one regression that can easily be extended to model multiple time series in a single regression analysis, okay? And then after the break, following the midterm, we'll start on a new topic, okay? That's related back to topic 3 we've done in semester 1 on causal inference. And thanks for coming here on Friday night, despite it's a week full of all midterms going on and off. So thank you. At least I'm not the only one that's recording my voice in this lecture theater. Okay. So let's look at the first question on Padlet. So here we have a statement that regressing one I1 process on another one could potentially lead to spurious regression. So this is related to what we covered on Monday. Okay, and this is indeed a correct statement, okay? When we regress two I1 process, like regressing one on another one, we never really know whether we sort of run into a spurious regression or not, because in reality, we never know whether two processes are indeed independent or not. So there's always a chance that we encounter spurious regression when we regress one I1 on another one, okay? And to check whether that is indeed a spurious one or not, one could either, run the regression on first difference, or you simply add a lag-dependent variable onto the right-hand side of the equation, okay? If the result changes significantly such that previously it was statistically significant, and then in the first difference equation or in the equation where you included the lag-dependent variable, it becomes insignificant, that's signaling that you might have encountered a spurious regression originally, okay? So this is a true statement. Whenever we run the regression of one I1 on another, just the level, okay? So whenever we run a regression of this form, we always have the chance of risking a spurious regression. So this is the first one. Now the next one. Spurious regression can be easily identified and corrected by simply adding more data points to the time series analysis. Okay. So do you think that increasing the sample size T could fix the problem of a spurious regression? Okay. This is a false statement. Okay. If spurious regression could easily be data points to our sample, then we wouldn't be so worried about encountering a spurious regression, okay? The fact that we have a spurious regression will not go away no matter how large the sample size is, because it's not the sample size that's triggering the issue. It's the stochastic trends in the time series itself that is triggering the issue, unless we can somehow control for the stochastic trends, okay? Otherwise, we won't be able to fix the problem. We can't resolve the spurious regression just by simply adding more data points to the time series, okay? The OLS estimator is inconsistent no matter how large the sample size is. When we have a spurious regression, the beta hat 1, okay, on the slide, it does not converge to true value 0 as the sample size increases. And the t-value will remain large regardless of how large the sample size, and the R square will also stay quite large. okay? So this is incorrect. Either you balance both sides of the equation by the same stochastic trend, so that's by including a lag-dependent variable on the right-hand side, or you run regression using stationary time series. So this is the second one on spurious regression. The very final one is related back to our ADF test for unit roots. So here what it says is, in an ADF regression, using 2 legs of the first difference of yt, so including 2 legs of the delta yt on the right-hand side, in an ADF regression, aims to test for a unit root in a time series yt that follows an AR3. Okay? Do you think this is correct or wrong? Now, this is a correct statement. Okay? So essentially, the ADF regression here, where we use the delta yt, the first difference, as the dependent variable, and we also include 2 legs of the first difference. On top of that, we also have the immediate lag for the level. This is the ADF regression for testing whether the yt following an AR3 has a unit root. Okay, these 2 equations, they are mathematically equivalent. You can transform the AR3 to the ADF form, or you could convert the ADF form back to the AR3. To see why this is the case, okay, we simply just need to check that the 2 regression involves exactly the same terms. So in the ADF regression, the dependent variable is the difference between yt and yt minus 1. Okay? On the right-hand side, we also have a yt minus 1, and then the first difference first lag is yt minus 1 minus yt minus 2. And the second lag is the difference between yt minus 2 and yt minus 3. Okay? Essentially, the ADF regression is a function of yt. And imagine if you take yt minus 1 on the left-hand side to the right-hand side of the equation, rearranging the terms. On the right-hand side of the equation, okay, you have yt minus 1, you have the yt minus 2, and you also have the yt minus 3. Okay? So essentially, these 2 are the same equation, just in different forms. The pi and the gammas, okay, they are functions of the alphas. So keep in mind that the ADF regression is for testing a unit root in the level yt. It's not for testing a unit root in the delta yt. If we were to test for a unit root in the first difference, okay, to test for a unit root in the delta yt, then we need an ADF regression of the form where we have delta square yt as the dependent variable. Okay? It's the first difference of the first difference. So it's the second difference as the dependent variable. And then we also have an intercept, okay? And then we'll have the pi, which is then a slightly different pi. Okay, let's call this pi prime. And that is multiplied by the delta yt minus 1, okay? And then you plus, some, let's say, gamma prime, delta square yt minus 1, maybe plus another lag and plus the error term, okay? This is the ADF for testing a unit root in the first difference, okay? One way to easily sort of check the ADF regression is for testing a unit root in which one is by looking at the dependent variable and also what is multiplied to the pi on the right-hand side, okay? Here, the dependent variable is the second difference, but the pi is multiplied to the first difference. So it's for testing a unit root in the first difference. Whereas this ADF regression on the top, we have the first difference as the dependent variable, but pi is multiplied to the level. So this is the ADF regression for testing a unit root in the level. Okay? So that's the main difference here. So the statement on Padlet, okay, this is a correct one. So that's sort of to quickly wrap up on what we have done so far. Okay, so coming to the slide for today. So far we've been talking about how to check for non-stationarity. So essentially this entails first doing some preliminary examination, eyeball test, okay? But any eyeball test conclusion is not a formal conclusion, okay? Any firm conclusion has to be associated with hypothesis testing. So if we sort of kind of identify there might be some trends in the time plots, then the next step is we use the ADF test for the level or the first difference to determine the series order of integration, or equivalently we want to determine how many unit roots or how many stochastic trends YT has. Okay, so we'll continue. So we start from the general to specific procedure for the level, okay, and then we follow a sequential approach to determine the order of integration. And we stop the sequential approach until we continue the sequential approach until we find a rejection, okay? It's obtained for some order of differences. And there we will conclude that the YT is integrated of order D, okay? If we stop the test at, for the D difference. And typically, as I mentioned, in reality, economic time series are either I0 or I1. Really rarely you will see I2, let alone I3. Okay, so usually D is equal to 0, which means that the underlying time series is already stationary, or that D is 1, which requires differencing ones to achieve stationarity. Then, if we have identified a time series as I0, which is inherently stationary, maybe around some deterministic trend, okay, then we don't need to do any differencing. We just model the underlying stationary series directly, possibly with a deterministic trend, okay? If we have identified that it's integrated of some order D that is greater than 0, then we would model the stationary transform series, okay? So always run the regression on the stationary form. And it could be that apart from having stochastic trends, there's also structural breaks in the underlying time series, which is also a type of non-stationarity, okay? And typically, it's very hard to identify where exactly that structural breaks happen. So instead of using the child test, typically we use the QLR test for the breaks within the fitted AR models, okay? So if no breaks found, then you can proceed with forecasting. If you found a break, okay, if you're just interested in describing the data set you have, then you just incorporate the breakpoint dummies into the model for the break date that you have identified using the QLR test. Or if, on top of describing the underlying time series, you also want to do some forecasting, then typically just model the most recent stable data and use it to run forecasting, okay? So that's sort of, given a time series, how can we sort of achieve to its stationary form? And imagine we have multiple time series, we'll do the same for all time series, okay? We want to make sure that they arrive at their stationary form. So what we're gonna do today is, we'll assume all the variables in the regression analysis are stationary. This is either they are inherently stationary, no breaks, I0, or it could be that you have achieved stationarity through some form of transformation. And remember, the ARP model that we have seen so far is always the benchmark. What we're thinking about at this stage is how we can improve accuracy beyond the ARP model. So the idea is we want to adjust the ARP model by including more lags of variables coming from another time series that's of economic or practical relevance. Now, one thing you have to keep in mind, we should not exclude the lags of the YT. Okay? Even if you're including lags from another time series, you should keep all the lags for Y that has previously been included in the AR model. If you have excluded that, that might adversely affect your model accuracy. Okay? So coming back to where we have seen earlier, okay, we've been talking about the GDP growth, and previously we've seen that the BIC and the AIC, or even the stepwise testing procedure, they indicate an optimal lag order of 2. So AR2 seems to fit the GDP growth the best. Now, from the plot, okay, where we have plotted the actual data in blue and the fitted AR2 in red. So what we can sort of see here is that the AR2 seems to capture the central tendency, okay, the long run average quite well, but it falls short in capturing the volatility. So essentially, this suggests that there is some missing dynamics in the model. But this is the best we could do with an AR model. Okay? Then how can we improve on top of that? We need to consider bringing in some extra information carried by different time series. So what we're going to do today is we're going to incorporate additional variable coming from a different time series, the term spread. Okay? So according to macroeconomic theory, the term spread has sort of forecasting or explanatory power regarding the recession. So essentially, the term spread is the difference between long-term and short-term interest rate. So what we're going to do today is we're going to try to evaluate whether incorporating term spread might help us to improve the model's ability to forecast or to predict the GDP growth. Okay? So before we look at how we incorporate that into the GDP growth analysis, we need to first consider or discuss the theory. So essentially, the model where we have included variables coming from a different time series is called an ADL model. It's the autoregressive distributed lag model. So the autoregressive is the AR part. Okay? The distributed lag is the part referring to the lags coming from a different time series. So an ADL model of order PQ means that we include P lags of Y and Q lags of another time series, say X. So basically, we just extend the ARP model we had previously with Q more lags of X. Now, this model, okay, we can include the current XT alongside its lags for border context. Okay, so here, we haven't yet inserted a beta naught times XT. You could do that. That's still an ADLPQ because we still have P lags of Y and Q lags of X. Okay? So the Q is the number of lags, whereas XT itself is not a lag. Okay? So including or excluding the XT doesn't matter for whether the model counts as an ADLPQ or not. So some examples. So an ADL21 basically means we have 2 lags of Y and 1 lag of X. Okay? So we have YT minus 1 and YT minus 2, and we also have the XT minus 1 on the right-hand side. Now, one thing you have to be careful about is if you add the current XT, but you drop the lags of X, that violates the ADL structure. It's no longer an ADL model because there's no lags of X. Okay? This is simply an AR model with an additional variable X. Okay? So the model we have here, where we have the beta naught XT, but dropping the beta 1 XT minus 1, this is essentially an AR2 with XT. Okay? Whereas, if you have this ADL21, okay, and you've decided to add an extra XT term, okay? This is still an ADL21 because it has 2 legs of y and it has 1 leg of x, okay? Whereas the one on the slide, dropping the leg x, is not an ADL, it's only an AR. And we could also have an ADL01, okay, which means you include no legs of y, but you include 1 leg of x, and that simplifies to a distributed leg model because there's no autoregressive part, okay? So this is called a DL1, or if you included 2 legs of x without any legs of y, then that's a DL2, okay? So autoregressive is the AR part. Distributed leg is the part of the leg of x coming from a different time series, okay? So the assumption for u, the error term, okay, it's similar to what we've seen earlier. We still assume that the u, the shock, is independent of all past information up to time t minus 1, okay? So the shock ut is independent of all the past information carried by y, that curly yt minus 1, okay? And the curly xt minus 1, which captures all past information of x up to time t minus 1. Now, if in a model where we also included xt, then typically we will assume that the shock ut is independent of all the information in the past for y up to t minus 1, but we will also assume that the u is independent of the current x. Okay, the one thing I'll be careful in this model, okay, which means in this ADL model, what we will assume is that ut is independent of the information for y up to time t minus 1, but information for x up to time t. Now you might wonder, why don't we assume ut being independent to all the information up to time t? Is this plausible? Can that ever be the case? No, right? Yt depends directly on the shock at the same time period, okay? We can never assume ut being independent of information for yt up to time t. It has to have a lag between the u, the shock, for the y series and the information we have for the y series. Whereas x, it comes from a different time series, so it's safe to assume that ut is independent of xt in the same time period. Apart from that, it's independent to the past of x. Okay? So this is the assumptions that we made for the shock. Okay, given independence is the strongest form of no relationship, this basically implies conditional mean independence. Okay, so the conditional expectation of the error term given past information is 0, or if we included x, then it's the conditional expectation of u given past information of y, and information of x up to time t is 0. Okay, that basically comes from the independence. Independence is the strongest form of no relationship. So independence implies conditional mean independence. Then, given conditional mean independence, then this must imply that the conditional expectation of y is, given the past, is fully determined by the p legs of the y and the q legs of x, and also the xt itself, if included. Okay? So what we're saying is, imagine for the ADL21 model here where we have the xt, the conditional expectation of yt, okay, here it's given all pass for yt, okay, and that's all the information of x up to time t. Then the first thing we do is we plug in the model equation for y, which has 2 legs of y, and the current x, also the lag of x, and also the error term, okay? So first of all, alpha not constant, doesn't matter, okay? We can just take it out of the conditional expectation. The conditional expectation of constant is always itself. And for the second term, okay, the yt minus 1, it's contained in the information set, the curly yt minus 1. So the conditional expectation of itself given itself is just itself. The best prediction we can make about one variable, given that we have information for that variable, has to be the variable itself. So this is alpha 1, yt minus 1, okay? And similarly, yt minus 2 is inside the curly yt minus 1. So this is alpha 2 yt minus 2. Now for xt, given that we are conditioning on all of the information for x up to time t, okay? Xt is inside this information set, so the best prediction of xt is just itself. Again, we can just take it out of the conditional expectation, and similarly, its first leg, okay, it's already given in the information set. So what remains is the error term, but we have just seen that it's conditional mean independence given the past of y and also information of x up to time t. Okay, so this is the conditional expectation. The conditional expectation of y, given that it follows an ADL21, it incorporates 2 legs of y and just 1 leg of x. On top of that, because the original model has the current xt, we also include the current xt in the conditional expectation. Okay, this is because the shock is conditional mean independence of the curly yt minus 1 and the curly xt. Okay, this is basically just extending what we've seen earlier for one time series to multiple time series, but nothing really technical has changed. So this is the example on the slide, okay, is the one where we don't include the current x. So basically, conditional expectation just depends on the lags. Now, given independence, that implies conditional mean independence, that will in turn imply orthogonality, okay? So that means the parameters of the ADL model can be consistently estimated using OLS. Okay, so this is the model structure and the assumptions. Now, the model selection, basically the same as AR process. Okay, you can either using the stepwise testing. So here you have to do stepwise testing for P and Q separately. Okay, so but the stepwise testing for Q follows the same logic as the stepwise testing for P. You start from the highest possible order for P and Q, and then you gradually decrease 1 depending on the significance of the highest lag. Okay, so for example, we start with an ADL23. Okay, so the highest number possible for Q is 3. We run this regression, and if the xt minus 3, the third lag of x, is statistically significant, then that indicates Q equal to 3 is the optimal, okay? Whereas if the lag 3 of x is insignificant, okay, we drop this, and then we re-estimate the model with Q equal to 2. Okay, we stop this until the first rejection occurs. That gives us the optimal P and Q. Or instead, we could just calculate the AIC or BIC and find the model that gives the lowest value of these two information criteria. Okay, this might be simpler in the case when we have an ADL model, because this could be done by the program itself, whereas the stepwise testing down, we have to do it manually. So one thing to keep in mind is that an ADL model inherently has more parameters to be estimated compared to an AR model. Okay? An ARP only has P plus 1 parameters, whereas an ADLPQ has P plus 1 parameters. On top of that, another Q parameters to estimate. And The forecasting is the same as before. Okay, remember we aim to minimize the MSFE, and we have already established that regardless of the model we use to model Y, the optimal MSFE minimizing forecast is always the conditional expectation. It's just that the functional form of the conditional expectation would depend on the model we use to describe Y. Okay, if we describe Y using an AR model, then the conditional expectation will take the form that adheres to an AR structure. If we model Y using an ADL model, then the conditional expectation will adhere to an ADL structure. Okay? And one thing you have to be a bit careful here is that if we're interested in forecasting, okay, think about what it meant by forecasting. We are using the past to forecast the future. So we want to forecast future YT using past information of X and Y. Then typically we'll exclude the current XT in forecasting, okay? So the one step ahead forecast basically is just a conditional expectation of Y given the past information of X and Y. All you need to do is, okay, given the conditional expectation we have found here, it's just that now we don't have this XT term, okay? And all you need to do is to change the notation, the lowercase t to uppercase T plus 1, okay? That's it. So, which is why the optimal forecast, one step ahead, is the alpha naught, okay? The same as what you have here, the alpha naught, and the alpha 1, Y capital T, okay? That's because here when we swap the notation, we have Y capital T plus 1 minus 1, okay? Then you get Y capital T. And also you have alpha 2 times the Y capital T minus 1, because here you have Y, okay? T plus 1 minus 2, that gives you Y capital T minus 1. Then there's no XT, and for the lag of X, that's X capital T plus 1 minus 1, so it's the last observation of X that matters in the one step ahead forecast. And the feasible forecast is just you plug in your estimates, okay? Now, what can get a bit complicated is when you do multiple step ahead forecasts, okay? So that will require us to forecast the values for X as well. So imagine if you have the two-step ahead forecast here, okay? So we have the one-step ahead forecast on the right-hand side for Y, okay? That's basically coming from this equation, okay? We don't need to do any additional forecasts, but we also need a one-step ahead forecast for X, okay? So that means we require knowing what functional form it takes. So we need to specify an equation for forecasting S. It could be that X follows an AR2 and AR3. It could be that it follows an MA1, MA2. But you need to specify some function for X in order to forecast its future values, okay? So applying what we have seen to the specific data set, the growth and the term spread. So the term spread here is the difference between 10-year and 3-month bond rates. Okay, so the difference between the long-term and short-term interest rates. And we have estimated an ADL21 model. Okay, so basically we just add a lag of X. And this gives us the fitted OLS. Then using the final observation, okay, so the last two for Y and the very last one for X, we can compute the one step ahead feasible forecast, basically kind of similar to what we have seen earlier when we're forecasting using AR models. Now, the question is, given that we model Y using an ADL21, what should be the optimal long-run forecast? Would that depend on the ADL model structure or depend on something else? Okay. Remember, the long-run forecast is about how the forecast evolves as h converges to infinity. And that's, given we know the growth is stationary, okay, any stationary time series in the long run, we expect it to converge it back to its long-run equilibrium, its expectation. So regardless of we model it using an AR3, AR4, ADL21, ADL52, ADL5, in the long run, as h goes to infinity, the long-run forecast for the y is always its long-run mean, okay? Basically reflecting the fact that a stationary time series is mean reverting, okay? So regardless of the model, optimal long-run forecast is the long-run mean for a stationary time series. It's just that the short-term forecast would depend on the model that you use to describe the underlying time series. Okay? So if we now add to the figure we've seen earlier, also the fitted ADL21, okay? The question we want to ask here is, does including the term spread really helps us to improve the explanatory power of the model compared to having a pure AR one? Okay? If we look at this, yeah, we can to some extent argue that maybe it captures the volatility a bit better, although it doesn't really seem like to be the case. We don't know. Okay? Then we need to test this formally. So this basically leads us to examine Granger causality. Okay? So Granger causality is perhaps the only new term today. Basically, we want to ask, does the term spread Granger cause the GDP growth? So Granger causality is about whether the lags of X, okay, adds explanatory power for modeling Y beyond what has already captured by the lags of Y itself, okay? So the definition of Granger causality is X Granger causes Y if the past values of X help explain the current values of Y beyond the past values of Y. So this Granger causality, okay, it's about predictability, okay? It's still a descriptive concept. It's not causality in a strict sense. That's why it's called Granger causality, not causality. It's sort of a causality concept proposed by Granger. That's why it's called Granger causality. Maybe a more appropriate term here is called Granger predictability. Okay? It's about predictability, not about causality. We want to know whether lags of X improves the prediction of Y, okay, on top of that, based on the lags of Y itself. So one thing I have to keep in mind is that Granger causality is a time series specific concept. Basically, this idea based on the fact that the time does not run backward, okay? There's only one direction when we think about time. If an event A happens before another event B, it can only be that A might affect or A might cause B, but it can't be that B is causing A because B happening after event A. So Granger causality doesn't imply the true causality, okay, but only suggests the potential causative relation. If the past happens before Y, it could be that the past is causing Y. We don't know, okay? But what we can say at best is the past helps explain the future Y, okay? That's why it's about predictability. It's about explanatory power, not about the true causation. So for the ADL21 model, okay, then basically the coefficient on the lag X, the beta 1, measures the lag X influence on Y. On top of that, carried by the lag of Y, the alphas, okay? So if this beta 1 is 0, then basically it means X does not help explain Y beyond the lags of Y. So X does not Granger cause Y. If the beta 1 is different from 0, then it means X does Granger cause Y because it carries explanatory power for y beyond what's carried by y's lag. So essentially testing for Granger causality. It's about testing for statistical significance. It's just that the name or the term Granger causality sounds new, but the underlying intuition, it's just the same as what we have discussed all the time. It's about statistical significance of some coefficients, okay? So why does this matter? For econometricians or for statisticians, okay, we care about model simplicity. We want to know whether we really need an ADL model or an AR model suffices to capture the underlying dynamics in Y. Okay, so is X necessary to be included in a model equation? Whereas for economists, okay, they seek for some theoretical theory, okay, whether one economic variable helps us to forecast another economic variable. Okay, so it's about statistical significance and practical significance. So, sort of wrapping up the Granger causality, okay, the general setup. If we have an ADLPQ, so an AR part and the distributed lag part, okay, the Granger causality is about testing the betas. Okay, we want to test whether all the beta 1 to beta q are jointly 0. Okay? Under the note, they are 0, no statistical significance, no Granger causality. Under the alternative, at least one different from 0, there is Granger causality. So inherently, there are Q linear restrictions. So if Q is 1, which means we have an ADL P1 model, we could use T or F test. If Q is greater than 1, multiple restrictions, F test. Okay, so always under the null hypothesis, our restricted model is the AR model. There's no distributed lag part. We omit all the lags of X in the restricted model. Okay, whereas the unrestricted model is the ADL one, the ADL PQ. So there are a total of, I think there's a typo there. It's M equal to P plus Q plus 1 parameters, okay? So then what we need to do is just compute the F statistic. It could be the RSS form, or it could be in the R squared form. And here, given that we have stationarity, okay, under the null hypothesis, standard inference, you can find the critical values from a standard F table. And if the F statistic is greater than the critical value, we reject the null, which suggests X Granger causes Y. Remember, F test is always a one-sided test. Okay? F test is always an upper tail test. You only reject the null if your test statistic is greater than the significance level. Whereas the ADF test, okay, that's a lower tail test. You will only reject the null if your test statistic is smaller than the critical value. What does it mean by that? Your test statistic is more negative than the critical value. Okay, that's for the ADF test because it's a lower tail test, whereas F test is an upper tail test. Be careful, like which tail you have to look at. Okay, so the very final slide. Basically, okay, how can we test whether term spread Granger causes the GDP growth? Then in the ADL21 model, that's about testing whether beta 1 is 0. So we can see from the output, okay, the T statistic is 2.5. Or we can compute the F statistic, which is the square of the T, okay? And given that the T is 2.5, that is greater than the conventional significance level, the conventional critical value at 5%, which is 1.96, okay? So since the T statistic is greater than 1.96, we reject the null. So the term spread thus Granger causes the GDP growth, okay? If instead we model an ADL22, then we can no longer use the T statistic, and we need to use the F test, okay? So ADL22 incorporate 2 lags of X. Then testing for Granger non-causality, so the null hypothesis of the Granger causality test is that beta 1 and beta 2 jointly 0, okay? So the left figure is the regression output. The one on the right gives you the F-test results. And you can see that the F statistic is 4.6. Okay? And to find the critical value, basically, you just look at the usual F table. Given that we're testing for 2 restrictions, so we should read the value on the row where we have n being 2. For 5%, the critical value is 3. Okay? So since our F statistic is larger than 3, okay, the F statistic is 4.6, that is greater than 3, which means we would reject the null hypothesis at 5%, again confirming Granger causality. Okay, so that's it for time series. Thank you so much for coming today. I hope you guys have a good break. And maybe you already seen my announcement this morning. I've got some good news for you that you have a wider window to do the midterm test, although it's still a strict 45-minute plus a strict 5-minute for the bonus. Okay? Check my announcement for the midterm update and everything you need to know about the Easter break. Okay? So thank you. I will see you after the break.